So now we have computed these degrees of freedom. It's 254, a big number. When the number of these degrees of freedom is large, it almost becomes normal distribution. You start seeing difference only at the third decimal, but we can still use the t distribution. To test this, the hypothesis, we can now reject H naught if, wait, there's a question. So Ali Zain has asked that will the exam be take home or physical? I think I wanted to do it take home, but I think there has been an order now that all exams will be on campus. So we don't have a choice in it. So unless something goes drastically wrong with the COVID situation, and there's an order from the institute that we can again take home exams, or if they ask us to take home exams, just assume that it will be on campus, because currently this is exactly what the orders are, that the final exams have to be on campus. I'll send an email about it as well. So we can reject this hypothesis if, so we have a t variable. Our hypothesis puts the t variable at exactly 0, because that's how we have constructed it. Remember, this is the t variable. And according to our hypothesis, the difference is 0 or less. And we will reject it if we see, instead of 0 or less, if we see something much higher than 0. If we see something here with some critical value defined by alpha, which gives us the significance. Reject H naught if this variable sigma n square over nx, sigma m square over nm, sigma w square over nw is greater than this critical value. This is the degrees of freedom, and there's some critical value here, where as before the critical value is defined that when this variable, the probability of getting something beyond this critical value is equal to alpha. Now, in the beginning, I didn't say anything about what significance we want to do this. I just said, let's test it. So what I can do is, I know that I got a value for t which was not 0. How do I know? Well, I should compute it first and see what value I got in my, so what number I got for this thing. So when I compute it, I have 85.8 minus 71.5 over these two numbers which I had already computed, Sm square over Nm here and here, (2.424 plus 1.378). So give me something like this. So it's 7.33. So I directly, what I do, instead of finding that if this is bigger than the critical value for a certain significance, I can just compute the I see that I got some evidence. T is not 0, T is bigger than 0. How much bigger? That will depend on if I really have a result or not with any given significance. So since I got a number which is bigger than 0, somewhere here, so let's just compute its p-value. So remember, how do you compute the p-value? The number you observed, you just put it equal to your critical value and then compute how much probability you have here by putting this equal to your this variable, whatever you observed. In this case, I got 7.33. So p-value is just the probability that this t 254 is greater than this variable which you are computing. From your sample data. And this we got at 7.33. So what would this be? Well, in this case, I don't even have to look up at a table. You can go and look up and try to look it up in a table or compute it using SPSS. But anything which goes beyond 3 is practically 0. Seeing a number here for t or for z, which is like in the range of 5 or 6, 6 is already, you have a 1 after 6 zeros. So that's like 6 sigmas. If this is your 0 for z and t is not much different, this is, you have first sigma, second sigma. So for the normal, for the standard normal, 6 means you are looking beyond the 6 standard deviations. And the probability over there drops to 1 in a million, something like that. So this is practically 0. So that means you have got evidence that H naught is rejected. We have evidence to reject H naught with a p-value which is almost 0. Up to 3 or 4 significant figures is 0. So that means extremely strong evidence. Remember, the smaller the p-value, more evidence you have to reject H naught in favor of H1. So that suspicion in the data that women managers have slightly less bias towards the, it's not about how much less or more bias they have, how positive and how much positive or negative opinion they have of minorities, because all it's saying is the difference 0 or more than 0? How much is the evidence for that? It's not telling you how bigger is the difference between male and female. It's telling you that there's a difference. And this hypothesis that female have less points on this test on average is established. The data is telling us that there's a huge amount of evidence for that because the p-value is very, very small. So any question about this? Let's go to the next example. So suppose someone is doing a research and they look at the GPAs of l- students who are living on the campus and students who are day scholars, and this is what they find, that students who live on campus, they got 115 in this 114 in this sample, and the average GPA was 2.71. And in this sample, not everyone obviously had the same GPA, so standard deviation was of the sample was 0.64. While for the day scholars, they got 123 and their average GPA was 2.79 and the standard deviation was 0.56. Now they want to test the hypothesis. First of all, they have no reason to believe that one group has higher GPAs than the others. Well, you're seeing a slightly higher number here, but one has to test it. Does it have any statistical significance or if you see these numbers in the sample? So they start with this hypothesis that the population average for the on-campus students minus the day scholars is 0. And they're testing it against the two-sided hypothesis because they're not assuming anything in the beginning that which one they expect to have better GPAs. That this is not equal to 0. So that means this variable which they are going to create based on the difference of the samples, this is going to have a normal distribution and they're expecting it to be centered around 0. So if they see a number which is very large or a number very small, in both cases, they reject this hypothesis and accept this, that the GPAs of the two groups are not same. Let me see what's the question. This one. Now, we will again have to compute the t variable. And what you will say, we will compute the t variable, and if this thing, again the same variable, because again you don't know anything about the standard deviations of the population and you're not assuming them to be same. You're just using the numbers which you got from your sample. If it's greater than a critical value and if you have a significance alpha, you divide it between the two tails. If this is true or this is true, that this thing is less than the same critical value but with a negative sign, because remember this is a symmetric distribution. So if this area is alpha by 2 and this area is alpha by 2, then if you have this occurring at this number, then this will occur exactly at the negative of that number because it's centered around 0, the t distribution. Now first thing is just to compute the uh, degrees of freedom. So compute new for t new. Again, I will need these numbers. 5, I had computed this, but let me just check. 0.56 square divided by 114. Wait. 0.56 square divided by 123. Yeah, this number is correct. And similarly, I have SL square and L is 0.00359. So to compute this new, I will have 0.00255 plus 0.00359 square divided by 0.00255 square over 122 plus 0.00359 square over 113, because I have to put in one less than the sample number over here. And the same number which you computed comes here and the square comes down here. Now this thing I can call it. So when I add these, I get 0.00614 square and the same number here. But I'm going to write it like this: 6.14 into 10 to the minus 3 square and 2.55 square plus 3.59 square 113. And in both cases I had a 10 to the minus 3, which I have taken common. So this 10 to the minus 3 square and 10 to the minus 3 square, they will cancel, and I'll have 6.14 square, which is over 3. So this gives me 37.7, and downstairs I get 0.053 and 0.114. So I get 0.053 plus 0.114 divided by 37.7. Wait. divided by 37.7. So I get 255. So new is 255. So it's almost same as the previous one. So I'll be able to use those numbers. Now all I need to do, I can again compute the p-value. So p-value in this case would be the probability that this variable is bigger than, because I got a number for, if I compute this number, so if this is bigger than this and equal to this, where this is equal to xd, assuming that I got a number bigger than bigger than 0. You got a what value you got for new? Sarah, what value did you get?
Sir, I'm getting 3.77 over 6.14 to 10 square.
3.77
Over 6.14 into 10 square.
into 10 square. 7 over 6.14 into
Into 10 to the power of 2.
2. This is unlikely because this will give us a new which is 0, and I don't know, I mean, I think I did my calculation quite carefully. Let me see if there could be a problem. There's this number, this number. I don't see any problem here. I don't see any problem here. So 6.14 square is this. 2.55 square over 122. Can you do this? What do you get? 2.55 square divided by 122. I do get 0.053. 3.59 square divided by 113. I do get 0.114 or 5. So I think my calculation is correct. Anyway, it doesn't matter. Whatever the calculation is, you will get a number according to that. But I think my calculation doesn't have a mistake. Now, so that's what you do to compute the p-value. You put this equal to what you get from sample. So what do we get from sample? We get SD squared. I have to compute this number. I get 2.79 minus 2.71 over these numbers 0.00255, because it's the same numbers which I had here, plus 0.00359. So I get 1.020. So that means to compute the p-value, I will have t 255 greater than 1.02 is equal to uh, p over 2. But this number, I can just go and compute what this number is, and I get uh, 255. I get the value 0.15. That means the p-value is zero point 0.3. So although I'm seeing a larger number for the average of the day scholars, like over here, but the statistical significance is very, very low. P-value of zero point 0.3 is completely useless. That means there's a 30% chance if you reject H naught, if you reject this hypothesis that the averages of the two groups is same, then the chance of your rejection being wrong is 30%, which is a huge chance. So it's just a statistical fluke, just by a chance that you got a bigger number for the day scholars. That's what your statistical analysis is telling you. Now let's do another example. So suppose you have, again, let's take the same example which we did long time ago. You have someone takes a data of 25 couples, and for husband and wife, couple 1, couple 2, up to 25, he has some numbers for how many hours they put in for housework. They get the difference, which is hours put by wife, let's say XW, XH. They get these numbers, and what they find that the average hours put by husbands is 50, not hours, let's say minutes, in this sample, and the average minutes put by wives is 60. So that means this difference, average of the difference would be 10, 10 minutes. And they also find, using these numbers, every couple has a different difference. They find that the standard deviation of the difference is 20. And they want to test, conclude at zero point zero 0.05 significance level to prove or to show wives put in more time on average. So since you have to show this, so you start with this null, that the population average of wife minus husband is equal or less than 0, while the alternate hypothesis is that the population average, on average, all wives work more, is greater than 0. So again, as always, for your t, you have a 0, and if you see a number here, then you will reject it. Now, in this case, the data is correlated because I was able to make these differences. It was a difference for a couple, that how much the wife works and how much the husband works at home. Only then it makes sense to take a difference. Otherwise, it was, if it were a random man and a random woman, then their difference cannot be directly analyzed. It would have no statistical significance. It can be directly inferred from that. While for correlated data, the differences have the most information in them. So in this case, you compute for correlated data this variable of the differences. And it's the variable you computed from the differences, which again is a t variable because you don't know about the standard deviation of the population, has all the information which you need. Now, the critical value of t in this case of t is, since you have 25 sample size, so t is just 24 in this case, you're only looking at one column. These columns are irrelevant when you have correlated data. So you don't have to compute any averages, don't have to compute the degrees of freedom. It's just this sample on which you are doing your usual analysis. And since you have 25 entries here, so your degrees of freedom are 24. And you're testing at significance level of 0.05. So this five gives you this gives you the value. If you look it up in the table, this is 1.711. That's the critical value. So that means you reject H naught if d over st over under root n is bigger than this critical value. Now I can compute this. Twenty over 5, which is bigger than this. So we can reject H naught. At alpha 0.025. So there was enough evidence to reject H0 and accept H1, that the average hours put in by wives is more than the husbands. Now, suppose if our data was such that these averages were still same, so that the average of the difference is still 10, but data had for this SD, the standard deviation of the difference were larger. Let's say it was 30. So the numbers you were seeing were much more spread out. So in that case, can we reject? So then this variable would be 10 over 30 over 5. So 10 over 6, which is 1.66. And this is actually less than the critical value. So cannot reject H naught at this. So this shows that when you have more noise, more fluctuations, higher standard deviations in your data, then obviously the results which you are seeing that there's a difference has a lower statistical significance. That noise could have, that fluctuations could have by chance shown you that difference. While if the averages are tightly packed around a certain central value, then you have more confidence in, you can more easily reject or accept a hypothesis. We can also compute, if I go back to the original numbers, I can compute the p-value. Value would be that the probability of this variable is greater than the number I saw in my sample. This is just your sample average divided by, which is 2.5. This is your p-value. And if I compute this, I get 0.0097. So p-value is very small. That means I have a lot of confidence in this result. On the other hand, if the standard deviation of the difference were, previously I took it to be 20, if it were 15, so that the numbers are even closer in my sample, and that's why my standard deviation is small, then what happens to the p-value? Then this number becomes 3.3. So then the p-value becomes, is bigger than this number. And this number turns out to be 0.0013. And this is, you can compare with this. So p-value has reduced significantly. Why? Because the variance in the sample was smaller. So, any question? So, let me stop here and I'll upload these. I have to combine these two files and then I'll upload these.